So here they say a 12 kg block is initially at rest at point A at the bottom of a rough inclined plane. So when they say the incline is rough, we understand that it means there is kinetic frictional force. Okay. The block is pulled up the incline by a constant force F, which is acting parallel to the incline. The block reaches the point B, which is at a vertical distance, in fact, vertical height of 4.5 meters above the horizontal, with a speed of 2.25 meters per second, as we can see in this diagram. Okay. So we know that the initial velocity of this block is 0 because it was initially at rest. And we know that the final kinetic energy is 2.25 meters per second. The initial height is 0 meters and the final height is 4.5 meters. Okay. Now the first question says define the term non-conservative force. Well, of course, you can always do that. And the next one says draw a labeled free body diagram showing all the forces acting on this block when it is moving upwards along the incline. And we can see that it's 4 marks, which means you have to show us 4 forces on your free body diagram. And the mark allocation never lies for a free body diagram. 4 marks for forces and nothing else in between. So we go ahead and say, well, our object is represented as a dot, and the forces are represented as arrows pointing away from the dot. So in this case, we have the normal force here, which has to be perpendicular to the surface, regardless of how the surface is. Whether it's horizontal, vertical, whatever, it has to be perpendicular to the surface, as long as the surface is there. And we also have a force that is not compromising. Regardless of what is happening in life, it's always going directly downwards, always. And of course, we have the applied force. So it's applied parallel to the incline, and it has to be perpendicular to the normal force. So we call it force F. And since they said to us the surface is rough, we have a very jealous force, which always opposes the motion of an object. And in this case, it's the kinetic frictional force. So this is how the free body diagram is supposed to look like. But if we remember in the actual sense, how many parallel forces do we have along the incline? Well, we actually have 3 forces, right? Of course, we have 3. What are those 3 forces? Well, the first 2 you can already see, but there's always a force that is hidden if you're on your incline, and it's the parallel component of the gravitational force. Never forget your FG parallel. All right? Otherwise, that's what we say in Sesotho. So that's the free body diagram. I don't suppose you have any question, which is why I'm not going to ask you if you have any. You shouldn't have a question for the free body diagram. Now let's look at the next one. Now in this case, they say, calculate the work done on the block by the non-conservative forces when the block moved from point A to point B. Okay. Now the question is, how many conservative forces do we have in this case, which are actually doing work on your block? The normal force is not doing work, so we don't talk about the normal force because it's perpendicular to the displacement of the block. So it means here we need to talk about two forces, which is the applied force as well as the kinetic frictional force. But what is the problem if we want to talk about those two forces? Firstly, we don't know the magnitudes of those two forces. And we also don't know the displacement of this block. Because the displacement of this block is not really 4.5. It's the distance that is covered from point A to point B, okay? So we don't know that distance and we can't find it because we don't have the angle of the incline. If we did have the angle of the incline, then we're going to use sine and say the sine of theta is the opposite side, which is 4.5, and we divide it by the hypotenuse, which is the displacement. No, let's forget about that. It's not applicable in this case anyway. So what I'm saying to you is, since we don't know the magnitudes of these two forces, and we also don't know the displacement, which is covered by this block, then we have to use the formula that is exclusive to the non-conservative forces. Now, what is that formula saying? And it actually includes all those non-conservative forces. So it's finding the work done by all of them. So it says the work done by non-conservative forces is actually equal to the change in potential energy plus the change in kinetic energy. Okay. Now, what is the meaning of the change in potential energy? Well, it actually means, what do I mean it actually means? Hey, yeah, no. So we are supposed to say it's mgh final minus mgh initial, because we understand this is a formula for finding the potential energy, mgh. But of course, here you can see that since mg is the same in both of these two terms, you can choose to take your mg out as the highest common factor, and then you're left with hf minus hi. So let's do that in order to simplify our expression. So this is how we actually get the change in potential energy. All right. Now, what about the change in kinetic energy? Well, this one is supposed to be 1/2 mvf squared minus 1/2 mvi squared. And once again, since we can see that both of these terms, they have 1/2 in common, then this is what we are simply going to say. We say, okay, fine. 1/2 m is taken out. And here we have Vf squared minus Vi squared. And for this one, please don't make a mistake and end up saying it's Vf minus Vi, which is all squared. Yay! So you'll actually die a very decent death if you do that. Oh, please don't do that. Okay, so now we understand that for the change in kinetic energy, we can actually say it's 1/2 m into Vf squared minus Vi squared. So now we can go ahead and substitute. Well, the mass of the block is given to us as 12 kilograms. The acceleration due to gravity is 9.8. The final height is actually 4.5. And the initial height is 0. The mass is still 12 kilograms. The final velocity is given to us as 2.25, and the initial velocity is given to us as 0, because they told us that initially it was at rest. So now it's over to the calculator. So if you press this into your calculator, well, you simply get 529.2 for the first part. And pressing the second part, well, you simply get 30.375. And if you add this up together, well, you find that the work done by the non-conservative forces will be 559.58 joules, right? But of course, if you want to sound intelligent, you can just say Newton meter, like that. But just keep it simple and say joules. So the answer that you see here is actually the work done by the frictional force plus the applied force. So yes. And you should. Okay, so moving on, they say the same constant force now moves the block at a constant velocity across a rough horizontal surface from point B to point C, as we can see in this diagram. The force F acts parallel to the horizontal surface, okay? But listen to what they further on say. The magnitude of the constant frictional force acting on the block while moving from the point B to the point C is 42 newtons larger than the magnitude of the constant frictional force acting on the block when it is moving from point A to B. So now they say, calculate the distance from the point A to the point B. Okay. And here they don't specify what we should use in order to calculate the distance. Yeah. So you can use your energy principles because you understand that displacement is there in the network, for instance, or in the work done by any force, right? Yeah, we know it's there. Or you can use your equations of motion in order to find your distance. But let's analyze the situation carefully. Here they say, what are they saying? Well, they're actually saying the block is now moving at a constant velocity, which means that the applied force is equal to the frictional force. That's fine. And they also say to us, the frictional force when the block is moving from B to C is 42 newtons larger than when it is moving from A to B. What does it mean? It means we have added 42 newtons on top of the frictional force that we already had. Okay, that's fine. Remember what they also told us previously? They said it was at rest at the point A, and we also know its velocity when it is at the point B. And we also don't know the angle of the incline. Then it would be easy if we used the net work equals the change in kinetic energy. It would be very, very easy if we used that. Okay, quickly. Right, so according to what Njapase is saying, he says, we need to find the distance from the point A all the way to the point B, which is just the displacement along this incline, right? Okay, that's fine. Now, the first thing that he did here was to say, okay, fine. If we consider the work done by the non-conservative forces, we understand that there's actually two of them, the applied force as well as the frictional force. So he decided to separate these two works and say it's the work done by the applied force plus the work done by the frictional force. Then he came and said, but what is the work done by the applied force? How do we calculate it? Well, it's by saying the applied force itself times the displacement times the cosine of theta. And when it gets to the frictional force, it's the work done by the, It's the frictional force itself multiplied by the displacement, and then we say cosine theta like that. But of course, we already know what is the value of the work done by the non-conservative force. We found it to be 559.58. So we still bring it down, of course we do. And then we say, we don't know what is the applied force. But then we can see that looking at these two terms, we have displacement in common. Theta is not going to be the same. So we can take our displacement out as a common factor. Or maybe before that, we can just say we don't know the applied force, we don't know the displacement, but we know that the angle between the applied force and the displacement has to be 0 because the applied force is in the same direction as the displacement. Then we can also come back here and say the angle between the frictional force and the displacement has to be 180 degrees because the frictional force always opposes the motion of an object, always going in the opposite direction. So now we can see clearly that our 559.58 is equal to what? Well, here we have f times change in x. The cosine of 0 is 1. And of course, the cosine of 180 degrees, it's just going to be -1. Then here we can see that both of these terms, they have displacement in common. So we can simply take the displacement out. And then we can take the applied force and then we say minus Fk like that. That's fine. And we can call this one the first equation. Then where do we get the second equation? Well, they said to us when this block is moving on the horizontal surface, they said the frictional force that it experiences will actually be 42 newtons larger than what it was on the inclined plane, I mean. And of course, larger than means on top of the existing frictional force, we add 42. But they also tell us that the block is moving at a constant velocity on the horizontal surface. So he said, this means that the applied force will be equal to the kinetic frictional force plus 42. In fact, it's what you need to write officially. Yeah. If an object is moving at a constant velocity, it means the forces are equal to each other, but opposite in direction. And he said, since I can see F minus Fk there, I can also make this to be F minus Fk by taking the kinetic frictional force to the left-hand side. And now I have 42. Then he said, well, he's going to call this one the second equation. And he substitutes the second equation into the first, which means that every time he sees F minus Fk, he's now going to come and say, oh, well, we know that the value of this is just going to be 42. Then he said from this point, he's going to divide both sides with 42. And he found that the displacement is just going to be 13.32 meters. And guess what? He destroyed this without showing any signs of messing. Yeah, no. Thank you so much, Simon.